This is the screencast for section 1.7, example 1, forming functions from formulas. We looked a little bit at this in section 1.4, composition functions. We're going to expand on it here in 1.7. Example 1 asks us to write the area A of a circle as a function of its. So this part here, as a function of its, means when A is going to be the output, either the radius is going to be the input, the diameter is going to be the input, or the circumference is going to be the input. So for example, in part A, I want area as a function of radius. So the area where the radius is input. So I know that the area of a circle is pi r squared. So I'm already done with part A. Area as a function of its radius. So I plug in radius, I get out area. Now part B wants area as a function of its diameter. Well, I know that the diameter is twice the radius. So in other words, the radius is the diameter divided by 2. So if I take A of R and instead change it to A of D, that means instead of R, I'm going to put diameter over 2 squared. Or you could rewrite that as, let's see, d squared over 4, so that would be pi over 4d squared. So the area as a function of its diameter is pi over 4 times d squared. All I did was substitute, instead of radius, I put diameter over 2. Now part C asks us for the area as a function of the circumference. Well, I have to find out how circumference and radius connect because I have the area as a function of radius very easily. Well, I know the circumference is 2 times pi times the radius. So now I'm going to divide both sides by 2 pi. And I get radius is the circumference divided by 2 pi. So instead of A of R equals pi r squared, I'm going to do A of C, the circumference, and the radius as a function of the circumference is C over 2 pi squared. So similar to section 1.4, I want to find the area as a function of another variable. I've got to find the common ground those two variables have. So in part C here, circumference is related to radius, area is related to radius, so I could create that composition function area as a function of the circumference. And I can expand this out to be A of C equals, okay, so pi is going to stay here. That would be C squared over 4 pi squared. So simplified, that would be, one of the pi's would cancel out. So C squared over 4 pi is the area as a function of its circumference. The now try problem, number 19, says a sphere is contained in a cube. Okay. Tangent to all 6 faces. So that means that if I have a cube, which I am horrible at drawing, but if I have a cube, there is a sphere in here that is going to touch all 6 faces. That's actually not that bad for me. So let's work with that. First of all, we're trying to find the surface area of the cube as a function of the radius of the sphere. So I'm going to call let C equal the surface area of the cube. Well, I know the cube's surface area is going to be side squared That's one of the sides, and then there's 6 of those, so times 6. So that would be the surface area of the cube as a function of the side. So we'll call this the side. Well, I want to find the surface area of the cube as a function of the radius of the sphere. So let's make a connection between the radius of the sphere and the side of a cube. Well, if I look at the radius of this sphere, it's half of what the side of the cube is. So the side of the cube, the radius is 1/2 s. So now I can solve for s, multiply both sides by 2, and I get 2r equals s. So now I can plug in my formula for s and get the surface area of the cube as a function of the radius of the sphere. So instead of c of s, I'm now going to do c of r. And instead of s squared, I'm going to plug in the formula 2r squared times 6, which is really, 4r squared times 6, so 24r squared. So the surface area of the cube as a function of the radius of the sphere is 24r squared. So if I know the radius and I plug that in, square it, and multiply by 24, I'll have the surface area of the cube. The connection I made there was that I knew the surface area of the cube, and I knew how the radius related to the side of a cube, so I could make a composition function. As a result, the surface area of a cube is the function of the radius.